everyone. Hello, hello. It's me again. You should know me, Ethan Dhami, fourth year nuclear engineering student. And this is the second lecture that I want to give on distributions and counting statistics. So, last time we looked a lot at error propagation, why it's important, why you should know covariance. Today we're actually going to be doing a lot more stuff related to radiation counting. My spatula is not here today. Instead, I have this rocket nose cone, but I'm going to try and stick near the podium today, so we'll see how that goes. The recommended reading for today is Radiation Detection and Measurement by Noel. You were probably going to get recommended this in all of your other classes that have any form of dosimetry. It is the gold standard. Anyhow, let's get on with it. So pre-lecture question, again, it's going to be another which is greater. But this time, infinite $20 bills are infinite $5 bills. So place your bets now. Oh my God, that was laggy. What do we think? Now, obviously, at some point, having infinite money doesn't matter anymore, but which is greater? What do you think?
I think either is worthless because you're going to overinflate the currency.
That's so true. But which is greater? I'm not asking what would you rather have, which is greater? Does anyone have any intuition? What does your intuition tell you? $20, maybe?
Would they be equal? Because any number that goes to infinity becomes infinite.
Equal, because it goes to infinity. I like that. I like that. I see a hand over here. This guy's just struggling to laugh.
I just you did this because you're mean, so I say $5.
$5. Okay. So remember what you thought, and don't lie to me. Don't lie to yourself. Otherwise, you're not really going to get anything out of this example. But really, if we take a look at our limits, and let's say we divide the two amounts, and we'll see if we have a ratio between them. That way, we know if one is, say, 2, 3, 4 times greater than the other. We got to remember that infinity is a concept. It's not a number. Because any number you can think of, say 1e to the 56, 1e to the 56,000, doesn't even compare to infinity. No number that you could come up with in a definite amount ever compares to infinity. And in fact, you can have different degrees of infinity. If we look here, 20x squared, x goes to infinity, that's a larger degree of infinity than 5x. So by just saying infinity, I didn't actually define how big it was. And now if I got this question wrong on an exam, I'd be pissed. Frankly, I'd say it's unfair. You didn't tell me all the parameters that we're supposed to be looking at. However, what does this tell us about the way we think, or at least the way we're taught to think in engineering school? It's that you should try at least to provide an answer with the bounds that you're given. But sometimes, the best response to a question is another question. Sometimes you're given just enough information to solve a problem. If you're with Dr. Akita, likely you're going to be given a lot more information than you need to solve the problem, and it's up to you to sift through it. But in this case, and in some cases, especially in the real world, you will see that you do not have enough information to reasonably solve a problem without making assumptions. So, keep that in mind. Anyhow, moving on to today's plan, we're going to do a little bit of error propagation review, since we will be doing a bit more of it today in our examples. We're going to look at permutations and combinations, so a bit more statistics. Binomial distribution, then the Poisson distribution, which is of significant importance to nuclear engineering, and we will see exactly why. The normal and Gaussian, although we're not going to spend too much time on this because we're more interested in the Poisson distribution, followed by a question and review break. And I think the question review break is at slide 18 of 52, because we have some Gaussian confidence intervals we're going to talk about, and then a lot of radiation counting procedures and examples, because I think that is incredibly important to have, and you guys do not have environmental effects of radiation offered to your cohort, which is where this stuff would normally be. So, in the last lecture, we remember we had this lovely formula here, I think I was very clear and merciful in the midterm question I made. It wasn't too hard. No? Went fine? No? Okay. So that means I'll make these questions harder if Dr. Liu invites me to make more. Are there any questions on variance and covariance here? If none, then I just want to address one thing. I think Yvonne asked, why can this guy be negative? What happens if you square root it and get the co-standard deviation? And it could be a complex number. And the reason is, one response I'll say now, again, is that you don't ever hear of co-standard deviation for that reason. That's why we leave it as covariance. That's why we call it covariance. Versus variance, which is a real number. So other than that, we also learned that Euler's to the pi is greater than pi to the Euler's. But if that's all you got out from that pre-lecture example, I'm a little disappointed. The big thing I wanted you guys to understand was that in mathematical proofs, it's good to just take a stance. Whether it's wrong or it's right, just take a stance. And it makes your life a lot easier. And the other thing we learned, or that I asked, is if this variance of V here could ever be less than 0 from negative covariances. I doubt any of you did a proof for that. So unless you prove me wrong here, no bonus marks. Although I'll leave it open-ended in case you want to start doing it now, because I am dead serious about arguing bonus marks for you. If you can show me whether or not sigma squared V can be less than 0. So I'm going to try and blitz through a lot of the, the content here, because I do want to focus on our examples. Because I think looking at the radiation counting examples is going to be the most important part of this lecture. So, combinations and permutations. So how many ways can you order a set of items? Well, we denote a combination with NCR, where N here is the number of items in our data pool that we're taking from. C here stands for combination, and R stands for the number of items you are taking from that data set. So you're taking a combination of R items out of N things. Permutation, very, very similar. Permutation, the only difference is that it cares about how items are ordered. So I'm actually going to pull up the next visual here, and we'll talk about why they look a little different. So this is a permutation, R factorial, sorry, of n. So we have n minus 1, n minus 2, and so forth, all the way down to 3, 2, 1. Now let's say we only wanted to go to 4, so we don't want this 3, 2, 1 here. We want to pick n minus r objects. We're going to divide this by 3 factorial. That just gets rid of those last 3 terms, so that's where the permutation formula comes from. Now, if say you pick 5 items up, you don't really care how they're ordered. How many different ways do you have to order 5 items? 5 factorial ways to order them. So for all your permutations, you will have r factorial duplications of the same set of items, just in different orders. So that's why in combinations, when we don't care about the way they're ordered, we divide also by r factorial to get rid of those duplications. We're going to use some combinations more so than permutations in this lecture. So just remember that, that formula up there on the left. We're going to talk about the binomial distribution now because we're going to use it to define the Poisson and then talk about the Gaussian and talk about counting statistics. Who remembers what the binomial distribution is? Not surprised. I'm not a fan of the stats courses at this university. So to start proving the binomial distribution, or at least reasoning our way through it, we're going to start with probability trees. You all know what a probability tree is, I would hope. Yes? I'm seeing nodding heads. Good. So we have different outcomes, and we're going to follow these outcomes in branching paths. We're going to say there's a probability P of an event being successful and the opposite of that, so the event not really happening or being successful, is called Q. There's two options. The two options, something has to happen, so those probabilities must sum up to 100%, or in fractional terms, it just must sum up to 1. As you can see, you get a couple different ways of this happening, but if you look closely, and I colored the different events here, where Q is orange and P is white, you can kind of see some form of symmetry where you have 2 oranges here, 2 whites here, 1 and 1, 1 there, and then opposite. So the outcomes themselves are symmetric in a way. In fact, if P is 0.5, the distribution ends up being entirely symmetric, as we will see. So depending on the path you take, you will get a different probability of that outcome occurring. Let's say P is 0.1. Evidently, you're more likely to get a QQQ event than a PPP event, just because 0.1 times 0.1 times 0.1 is a lot smaller than 0.9, 0.9, 0.9. So if we actually look here at not necessarily the ordering of the outcome, we can kind of see a pattern. Now, the reason we can see this pattern is because it doesn't matter if you multiply 2 times 3 or 3 times 2, the order does not matter, it is still 6. So in fact, a PPQ and a QPP event have the same probability of occurring. So I've taken the liberty here to highlight in different colors the different sets of outcomes that have the same probability of occurring in this tree. As you can see here, we have 1 white outcome, 3 green outcomes, 3 blue outcomes, and an orange outcome. And if you are paying attention, or if you already know some combinatorics or Pascal's triangle, you'll notice that we can actually directly link combinations to these outcomes. So we have 3 different events occurring, one after the other. So n is 3. And we can choose how many of those are successful or unsuccessful. So for example, 3 choose 0, as in 3 events happen, 0 are successful. How many different ways do we have of that happening? 1. 3 choose 1, where 1 event is successful, so our blue events, there is in fact 3, and you can count them up yourself. 3 choose 2 is the green events. So as you can see, the green ones have 2 P events. And 3 choose 3, 1, for the one way you can have all of your events being successful. It's a little dull, I know, but we'll hopefully get this a bit more exciting as the lecture progresses. So we can write out these probabilities a bit differently. Because we're looking at X number of events happening, and we know that the sum of the P events and the Q events has to equal the total number of events happening, we can write the probability of a certain outcome occurring with this. N choose X, where X is the number of successes, and Q is the number of failures, or N minus X is the number of failures, times all the probabilities that it took to travel through that tree. In fact, this is by definition, well, we'll just put in the combinatorics formulation in there. This is in fact the binomial distribution. And very happily, it has a mu of n times p. That makes sense. Your probability of success times the number of times you run the event is the number that you're going to expect to get. And the variance on it is simply n times p times q. Very, very nice. I don't actually know what's on the slides after this point, so we're going to just play it by ear from here. So I believe I'm going to show a plot up here, and just note that all the plots shown in this lecture are very exaggerated because you get very small curves, so you have to magnify them to actually see the distribution of the curve on the width that we're looking at. So at p of 0.2, and a mean of whatever, this is what it looks like. Is this entirely true? No, because it's actually a discrete probability function. Why is it discrete? Does anyone have any indication why it's not actually a continuous curve? Seeing the gears turning.
Is there an asymptote at 0?
Well, there's an asymptote at 0, but that's not why it's not continuous. It looks continuous here, but in reality, it's not.
So the area is equal to 1.
The area is equal to 1, that's true, but the real answer is factorial. What's 2.2 factorial? Can anyone tell me? No, if you can tell me, you should go to Stanford for mathematics. Because you will blow their mind. No, in fact, we can't take a factorial of a non-whole number. So really what we have here is going to be a dot, and 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 a dot. And really what Desmos, which is what I used here, is doing is it's interpolating this curve. So in reality, it's discrete. So it's called a discrete probability distribution. At p equals 0.5, beautifully symmetric. In fact, it almost looks like a bell curve, which is not necessarily a coincidence. And we'll pump up to, I think, 0.8 here, where you can see that it skews to the other side. So the moral of the story here is that this probability distribution function can very much be skewed depending on the probability of success. Now, another thing that we can do here with these functions, and I think Dr. Liu was telling me she did some work on these, had some fun with it, is we can say that something either happens or it doesn't. And if it has a set probability of happening, that's a binomial distribution. Is there any examples that you guys can think of something that either happens or it doesn't, with a mostly fixed probability?
It rains or it doesn't?
It rains or it doesn't. That's a pretty good one.
Radioactive decay?
Radioactive decay. This guy's my roommate, so he's gonna know exactly what I'm gonna talk about later on. Are there any other examples? There's a lot of things that either happen or they don't. You know, you either get into a
We're either getting a mini quiz today, Jenko scores, or we don't.
That's a great one. You either get one or you don't. Exactly. So there's a lot of things you can describe with it either happens or it doesn't. So, spoiler alert, we're going to talk about radiation statistics. Now, when radiation either happens or it doesn't, what are we really talking about? What are we really interested in? Are we interested in a isotope decaying? Or are we more interested in actually measuring that decay? I think the answer is we're more interested in measuring that decay rather than it happening. So, how can we measure it? What can we do to really show this? Well, to do this first, we want to look at the Poisson distribution. And why do we want to look at this? Well, the Poisson distribution is basically the binomial distribution with a couple caveats. Number one, n is very large. When you're looking at radioactive decay, is n very large? Usually yes. How many atoms are in a mole? Many atoms are in a mole. What's the probability of actually measuring a count from a radioactive source? Like the absolute probability. It's quite low. So in fact, the Poisson distribution also follows this probability scheme, where the probability of success, i.e. measuring, is a lot smaller than the probability of failure, or failure to measure. And of course, mu is NP, which is a constant value. So this is the binomial distribution here. I've just taken the time to split it up really quick. I'm going to walk over here. We're going to talk about exactly what each term is. So big N. How are we going to express this mathematically? Limit to infinity. Very small p. How do we express this mathematically? P approaches 0 in the limit. Here's our combination term. So we're going to call this the first term, this is the second. This is our probability of success term, how many success probabilities in our path did we go through. And this fourth and fifth terms are split up for the probability of failure. So remember, it was q to the power of n minus x, so we split that up. And the other thing we did is we rewrote q to be 1 minus p. Any questions here on why this looks like the way it looks? Perfect. Okay, so we're going to go term by term, and we're going to see what these evaluate to in our limit. And I think I got lazy, so I didn't write the limit out for all of them, except for, I think, one of the cases where I felt wrong not putting the limit in. Okay, what can we do with 1 over x factorial? Not a whole lot. We're just going to leave that one for now. However, the second term, this one here, is in fact what? The permutation of x. In fact, it is, without that x factorial, it is n pick x. So of course it's n times n minus 1, n minus 2, dot, 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 all the way out to n minus x plus 1, because n minus x and all the other terms in the factorial disappear when you divide by n minus x factorial. Now, because this is n pick x, we have x terms multiplying each other. Now, another reason I chose the pre-lecture example to be the one I did is because here, it's a bit odd to use the rocket. I prefer the spatula, but oh well. Here, n is approaching infinity. So what's n minus 1? 1 is, for lack of a better term, pissing into the wind. So is 2, so is minus x plus 2, and so is minus x plus 1. No definite number, and x is a definite number, that we can come up with can ever compare to infinity. So really, we can rewrite this as n multiplied by itself x times, which is one of the simple ways to describe exponentiation. So that's a really nice simplification, I'm going to be honest. We turned all that factorial garbage into a simple n to the power of x. Now, if you remember our third term, it's also, in fact, to the power of x. And if we combine them using our exponentiation laws, we can rewrite this as mu to the power of x, or the population mean of the distribution to the power of x. Now that's very handy. So what are we going to do with the fourth and fifth terms? Well, let's see. The fourth term goes to 0, and when I like to prove this, I like to toss in a bunch of fancy algebra and other limit mess. But you can prove it just by looking at it. You say, okay, well, p is 0, so evaluates to 1 in the middle. 1 to the power of negative x is still just going to be 1. So fourth term disappears. It goes to unity. And the fifth term is fun, because we have 1 minus p to the n, 1 minus 0 to the power of infinity. Have any of you done the Euler's number proof? No, okay. So this we can rewrite as the limit of 1 minus mu over n. Remember, mu is np, so p is mu over n, to the power of n, which by definition, if you don't know the definition of Euler's number, I would highly suggest learning it and understanding it. But if you don't, I think I'll make that as a pre-lecture ramble for the third lecture I do, if Dr. Liu lets me have a third lecture. So this rewrites to be Euler's to the power of negative mu. And that's about all the 5 terms, that's about all the simplifications we can do. And if we combine all of these simplifications, of course the x factorial we couldn't really do much with, this is what we get. And this is a lot more palatable than the binomial distribution, in my opinion. It is simply the mean to the power of x over x factorial times Euler's to the negative mean. Is this going to be a continuous distribution? No, because we also have an x factorial. So what does it look like? That's the big key. What does it look like? Come on, do I have it? There we go. It looks like this, and this, in fact, looks a lot like the binomial distribution, because it's a special case of it. So this distribution very, very well describes events that have low probability of success, a lot of events happening, and of course it is discrete. That's your probability of a certain event x occurring for x successes. The mean, of course, is mu, which is interesting because the mean is in the definition of the distribution. And you can use the variance identity we derived last time I was here. If you try and use the definition of variance, it's really tough. So if you use that identity, you can show that the variance of the Poisson distribution is also, in fact, the mean. Now that's actually really handy. Why? I'm going to see what the next slide has. Why? So if we can use this to describe radiation measurements, because small x compared to n, and small probability of actually measuring based on the inverse square law and the efficiency of our detector, well, we only need to take one measurement, really. 1, 2, 3, doesn't really matter. We don't need to use the definition of variance to calculate variance. We can just use the square root of our mean to get our standard deviation. And that's exactly what we'll do later on. And there's no proof for this because there's a lot of math that goes into it, and it deserves a lecture on its own, in my opinion. But I've put here the Gaussian distribution, which we'll talk about briefly, but I think you all know what the normal/Gaussian distribution looks like, up here on the screen with the same mean and same standard deviation as a Poisson distribution. And as you can see, at the mean equals 2.3, fairly similar. At a mean of 6, we're really getting close to them being the same. At mu equals 20, it's a little absurd. And in fact, around mu equals 11 is when I would call it very, very similar and basically interchangeable. And of course, at mu equals 60, they're overlapping a lot. So you can imagine as the mean goes up and higher and higher and higher, the distributions look very similar. Again, Gaussian distribution is continuous. Poisson is not. But the interpolated curve is very, very much the same, and that is not a coincidence. You can, in fact, prove the Gaussian distribution from the Poisson distribution. It just takes a lot of effort and time. So we can take the Poisson behavior of radiation, and we can use that to basically calculate the standard deviation on our radiation measurements quite easily. So for example, I have this table here if you want to just verify with your calculators. So I didn't do this quite late at night. 121, 143, 135, some decent spread in the measurements, average of 133. So the standard deviation is root 133, which is about 11.5. That makes about sense. But I need you guys to see that we didn't have to use the sum of x minus mu squared over n to get the variance and square root that, of course, for our standard deviation. We didn't have to do that. We didn't have to go through all that tedium. It's in fact very quick to do this. Measurement, row 2, 14, 11, 23. Some decent spread. An average of 16 plus or minus 4. Now, we're not doing this because it's easy. We're doing this because it's correct. Same thing here, 52, 67, 49. And then, as you can imagine, 245 and 367, those high counts, with averages over 200, over 300, you can only imagine how close the normal distribution is to the Poisson distribution in this case. This will come up later. Actually, I talk about why it comes up later here. It'll allow us to perform Gaussian statistics on our radiation measurements. What are Gaussian statistics? Does anyone remember this sort of stuff you did with the Gaussian distribution? Vaguely. I'm seeing some nodding heads and confused faces. That's okay, because I'll cover it again. We'll look at it briefly before we actually start applying it. So this is the Gaussian distribution. It is also known as the normal distribution. Is this continuous, or is it discrete?
It's continuous.
It's continuous. And yet we proved it, or you can prove it, from a discrete distribution. It's very interesting, very interesting. There's some limit magic involved, of course. Now, does anyone know why we use the Gaussian distribution a lot in math and science and measurement? And the hint is right here. It's called CLT. If you remember what the CLT is. So really what the Gaussian distribution does is a lot of things that happen in nature tend to follow the Gaussian distribution very well. And in fact, with the central limit theorem, which I'm going to put here with a big red arrow in it, is that you can, with enough measurements, so at the cost of taking more measurements, convert any shaped distribution into a Gaussian, which is very, very powerful. But what does it cost? It costs a lot more of your time, a lot more of your energy, and the use of taking a lot of measurements, since you're, instead of doing statistics on the mean that you calculate. So you have to take multiple means. To take multiple means, you need to take multiple measurement sets. You can't just take one. Thankfully for us, you can count your lucky stars. We don't have to use it for radiation because our Poisson statistics allow us to assume a Gaussian shape at any measurable amount of counts.
I was just wondering how you know, given a set of data, how you know if it's Poisson or got like this one? Like which one is it? Literally just like one is discrete numbers, one is continuous numbers?
Are you talking about if you measure something in the wild?
Yeah, like if you have
Okay.
a set of data, how do you know that it would follow just by your data alone?
Just by your data alone. The first thing you would do, and a lot of old professors will tell you this, is you'll take out a piece of graph paper and you'll plot it. Because, well, let's do a thought experiment here. If you don't know the governing mechanics behind something, what are you going to do? So the only reason we know radiation follows Poisson statistics is A, measurements, and B, knowing the mechanics of radiation. So the first thing you should do when you have data is plot it. See what kind of distribution you're getting. Take enough measurements, you can convert, with the central limit theorem, your data into a Gaussian. Then you know it's Gaussian. And that's very powerful. That's why we do it. Because it doesn't matter what the original distribution shape is, with the central limit theorem, which would take a lot of talking about that I don't really want to get through today, you can convert it to a Gaussian. Other than that, look at the shape that it has, and then you need to figure out what the governing mechanics are of that phenomenon. Once you know that, you can kind of say, well, it's going to follow this, and the experimental data supports this theory, and then you're just in research, right? And that's fun. I like that. But yeah, so we know radiation follows Poisson because high x, or high n, low x compared to n, and a very small p. Does that answer your question? Okay, perfect, perfect. Are there any other questions at this point? Because I think we're reaching the midway break point. question break. Okay. After this point, I want to spend more time. That's why I kind of rushed through this section. I did want to introduce those distributions because knowing your distributions is important. Knowing why you can use Poisson statistics is important. If someone asks you, why'd you square root that number and get your standard deviation? And you're like, I don't know, and you're getting fired, right? That's also embarrassing if you're a nuclear engineer and you don't know why you're actually square rooting your number. So what have we learned? We've learned the binomial distribution. We've learned the Poisson distribution. We've learned some basic Poisson statistics that we can apply to radiation counting. And we've learned of the Poisson relation to the Gaussian vaguely and the Gaussian distribution. Are there any doubts? Are you not convinced of any of the math in here? Because we are going to do a lot of examples. I think there's 7 examples in the slides today. This is like slide 23. There's 50-something slides. So if you have any doubts, none? Okay. Hopefully, if there are any, we can address them as we do the questions. Before we get to the questions, I want to talk about Gaussian confidence intervals because we're going to be doing that in the questions. And by the looks of it, and what I suspected is that they're not well understood based on our university's statistics course. So there's a text wall. Let's read the basic idea of this. You don't have to read it all. It's your choice, not mine. Based on our mean and standard deviation, we can look at our Gaussian distribution and look at the probability of measuring a mean at a certain value. It does not tell us the mean is at that value with that probability. It is just that it tells us the probability we will measure that as our mean. Because once you know your true population mean, you can metagame your statistics. But if we could figure out our population mean with that ease, we wouldn't really have to spend so much time learning this stuff and learning why sample statistics are important. So based on the area under curve, I think you mentioned that the total area under a probability distribution must equal 1 because something has to happen. Well, we can look at how much probability we have in a certain interval and say, well, 95% of the outcomes are going to be in this range. Because you know those tails go off to infinity. If you want 100% of the outcomes, you have to be prepared for literally everything. So we call these confidence intervals, and we're going to talk a bit about how to get them. So, lovely drawing in MS Paint here. This is a Gaussian curve. And here we have the 95% confidence interval and the 99% confidence interval. As you can see, you have to go a bit further from the distribution to get that extra 4%. So is the juice worth the squeeze? It depends. So this blue area represents 95% of the outcomes. The pinkish area represents the extra 4% that it takes to get that 95 to 99%. And as you can see, if you want to get any higher percentages, the probabilities at the very tails are very low. So you're going to have to really, really stretch out your interval to get those probabilities. The reason I've highlighted 95 and 99% is because these are the most common ones, common intervals to work with. In fact, the 95% interval has a very nice and easy to remember number. So these are the intervals. 95% of a Gaussian distribution will be between the mean subtracted of 1.96, its standard deviation, and 1.96 plus its standard deviation. 1.96 is basically 2. That's really easy to remember. So if you have to remember any number, and this is why I have put an orange square around it, please remember 2 sigma. So that'll get you 95%. If you want to push it up to 99, you can see that for that extra 4%, you're moving up about 0.6 of a standard deviation. which is diminishing returns. But it's not unreasonable to have 2.58 sigma. As you can see, when you have larger count measurements, that square root really comes in handy because the numbers don't get egregious. When you have small counts, the square root becomes problematic. So, why do we care about confidence intervals? Usually we want to see whether or not our measurement in general, but especially for radiation, is above the number 0. i.e., do you have a statistically significant amount of radiation? This is of importance especially to environmental monitoring, where you want to check if there is radionuclide releases from, say, a nuclear plant, a lab, or even a nuclear accident. Is something contaminated? So usually we'll check a confidence interval greater than 0. As you can see here, there's this Gaussian confidence interval has a significant portion of its probability below the 0 line, which is mind-blowing. What this tells us is, say this was our radiation distribution curve, we would not be able to say with a high degree of confidence that, yes, there is contamination here. We could say it with whatever confidence we choose from here on, but maybe that's only 70%. Maybe that's only 80%. How do you quantify it? Well, if you're going to use, forget that happened, please. If you're using a two-sided confidence interval instead of a one-sided confidence interval, which we will use a two-sided confidence interval, your two-sided one is going to be more conservative of an approach than your one-sided. And there's the but why. Sorry, I was very tired. I don't actually know what's on these slides. Why? Why is a two-sided confidence interval more conservative than a one-sided? I think I prepared some plots here. Yes, I did. Let's look here. So one-sided 95%. So instead of going through the mean and going plus minus, we've just gone with the mean, subtracted an amount, and then summed all the probabilities up to be 95% from that point on to infinity. Okay, so we have this nice tail here that carries about 5% of the distribution. But what does it look like if it's a 95% two-sided? Well, look here. This area here on the one-sided distribution is not present in the two-sided. What this does is we're taking this area here and we're pushing it out to this side, which pushes our limit of where that 95% area comes in a two-sided interval further to the left. So if we're looking at a greater than condition, we want our marker on this interval. We want this limit of our 95% to be as rightward as possible. Taking a two-sided confidence interval is more conservative. We'll actually be taking it technically to a higher one-sided interval percentage. In fact, if you want the numbers for this, a 95% one-sided confidence interval is greater than the mean subtracted 1.65 sigma. That is less than 1.96, which we use for our two-sided. For 99%, it's minus 2.33 sigma, which is less than our 2.58 sigma for 99% on a two-sided interval. This was a lot to throw at you guys. Are there any questions? Does it kind of make sense? You can get an interval by taking the mean plus this much sigma minus this much sigma. See your range, and if it crosses 0, then you know you can't say with that confidence that there's radiation. And we'll do examples of this to make sure the point hits home.
Isn't the top graph more conservative because you have greater confidence in your upper bound than the lower graph?
let's say hypothetically, this is 0, right here, just to the left.
Right.
So you measured your radiation, this is your confidence interval one-sided. 95%, the interval is above 0 entirely. You have radiation. So the two-sided, bring this down. All of a sudden, the confidence interval now goes into the negative values, just by a little bit, just by a little margin. Which means that on the two-sided, you'd say, no, you don't have more radiation. It's more conservative in saying that there is radiation rather than there isn't, not conservative in the normal approach that you would say that we're going to assume that there's more radiation than there is. No. You have a question? No, he's good. Okay. Are there any other questions from this point on? Okay. So radiation counting procedures. As I said before, the topic of interest really is, and it's almost 12, so I'm going to speed up a little bit. Topic of interest is there radiation? Is it there rather than how much is there? Because sometimes you have contamination, but you're not worried about how much there is, you're worried if it's there. If it's not there, you don't have any reason to worry. If it is there, then you can start worrying about how much there is. So how do we determine what is a statistically significant amount of radiation? And if you're reading ahead in the slides or you're paying attention to what we were just doing, you'll know that we use confidence intervals. And I'm not seeing people getting excited for this. This is fun math, guys. Got to be excited. And I hope you all know what comes next. The answer is, but why? Why do we use these confidence intervals? Again, it's because we can say that, I'm sorry, I actually have no idea what's on these slides. I'm lacking a lot of sleep. So we usually check on, are we going to measure radiation with a mean above 0 95, 99% of the time? Because if you consistently measure the mean above 0, then you can safely say that, yeah, there's radiation. Mathematically, this is what a confidence interval is. So how do we do this measure? Can you measure background and total counts at the same time? One measurement, you get your background, you get your total. There's only one case where you can kind of do it. I say kind of, and that's in gamma spectroscopy. But if you just have a counting detector, absolutely not. You're not going to be able to differentiate what is background from what is a source. So this is why we take a background measurement. How do you get your net counts without background? Well, you take a total measurement, background and your source, and then you subtract your background. Because net is a calculated value and total and background are measured, there is going to be some error propagation. Now I want to take a little bit of time here. I'm sorry I didn't put it on the slides. But do we expect to get covariance, any amount of covariance, when looking at a total measurement versus a background measurement? What are we thinking here? Because if we don't have to worry about covariance, we save ourselves a lot of work. But if we do have to worry about it, we shouldn't neglect it, especially if it's our health at stake from our calculations. What are we thinking? Thankfully, no. You usually don't have to worry about covariance and radiation. Does the total measurement depend on the background? Yes, absolutely. Does that mean there's covariance? Not necessarily. If there's covariance, your source term in the total would be higher than normal when the background's higher than normal, or lower than normal when the background is lower than normal. So you take 5 measurements, background, 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 background. Then you take total, 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 total. Because you're not taking them at exactly the same time. You want to use the same detector, of course, to make sure everything is the same. Those fluctuations aren't going to correlate with each other. If you took them at the same time, which I said earlier you can't, When the background's higher, of course total is going to be higher, because it's a sum. When its background's lower, of course it's going to be lower. But then you also have to worry about the actual source fluctuations. Maybe the source fluctuation brings it lower when background's higher, and vice versa. And the big idea here is that your source radiation does not depend on the fluctuations in your background. If I have a cesium-137 source and I'm blasting you all with it, background isn't going to do anything to make it a stronger beam or a weaker beam. The background's just there. So thankfully, even though I taught you all covariance, and I do want you to keep it in mind, you do not have to use covariance in radiation counting statistics for the most part. Check for it just in case. Be paranoid. Be paranoid. But you usually don't use it. One example I can say of correlation is I was in the bunker the other day, and before I got my migraine that cut my lab short, we're taking the G10 gamma source. Have you guys been to the bunker yet? They've got a big lead box with a big gamma source in there. And we're irradiating 3 little rat-eye detectors, dosimeters. Consistently through all the runs we did, detector 1 always has the high count. Detector 2 always has the low count, and detector 3 is always in between the two. Consistently. Does that mean the radiation is selectively dosing the dosimeters? No, because we put them in a pyramid shape, but we don't switch them around. So the geometry of the setup wasn't affecting it. But the internal calibration of our detector was. Is there any way you can plot that for some covariance? Not really, because you'd be plotting counts versus detector ID. And at that point, you can just mix and match, and you can go, so there's a straight line going up because I put the lowest count rate detector first, then the middle one, then the high one. You could say there's a negative slope because you just arranged your data differently. Does that mean there's actually a correlation? No. So, bottom line, you're safe from covariance in pretty much all of these cases. And I think, we're going to get on to some examples. Let's see what this one is. This one is Gru from Despicable Me is accidentally dosed by his minions when a super gamma death ray they made suddenly activates on its own. Due to the frequency of these events, Gru has a dosimeter on him at all times. The dosimeter says he got a dose of 848 microsievert from the event. If dose is proportional to counts, that's a hint. That's what we call a hint, all right? Then what is the lower limit of his dose on a 95% and 99% confidence interval? So we're not looking for, is it greater than 0? He got dosed, 100%. And that minion, I think, is holding an employment application for a J*B, because I know that's a trigger word for some people. So we're going to do a 2-sided confidence interval for all of these. Sometimes you could use, I see people laughing, maybe something's funny. We'll do a 2-sided interval because it's just easier. We could do 1-sided, but it's good to be conservative. So what does this calculation actually look like? Do you guys want to try it out? Or maybe let's go through this one, you'll see the process, and then maybe through the other 6 examples that we're going to get through today, you can try it on your own. So number 1, we know that I'm not going to put units up because it was getting really late and I got really tired. Dose is proportional to counts, which is actually very true because it's gammas. So our sigma on our counts are 29.1 microsievert. Very simply, our 95% confidence interval, well, what's our mean? Do we all know what our mean is? It's 848. There's one measurement. Therefore, it's your mean. Is that good procedure? No. Does it work? Yes. So we're going to see a plus or minus 1.96 sigma for our 95% confidence interval. So 1.96 times 29.1 is going to be plus or minus 57.1 microsievert. For 99, 2.58. Now, I would write these two numbers down because you're going to be using them a lot if you want to follow along for the examples. If you just want to sit back and watch all the math I did for you, all power to you. It was my time, not yours. So okay, 75.1 plus or minus for 99%. So as you can see, the 99% interval is in fact a lot larger than the 95. That makes sense, right? You're going to stretch out the interval on your distribution. Looking here, we have 848 minus 57.1 because we're looking for the lower limit of his dose. So we don't care about the plus. We're looking at the minus only. 791 microsievert. And with a bit more conservation in our number, 773 microsievert. So Gru got dosed. All right, his days might be numbered. In fact, if this is a regular occurrence, like the problem says, he might not be long for this world. So okay, now you can tell him that as a nuclear engineer. You now have done this before. So if Gru gets dosed again, and again, and again, you can tell him that his days are numbered. Next problem. Are we good? Are there any questions on this one, or does it make sense? Yeah, it makes sense? Do you guys think you can do the next one? Feeling confident enough? Just bite the bullet. Doesn't matter if you're wrong. Once you start putting pen to paper and trying something, you'll learn a bit more than if you were just listening and not following along. All right, next example. You're visiting Chernobyl, and your dog runs away into the Red Forest. Who knows what the Red Forest is? I think Ivan's laughing. I see a couple of people. It's where they buried a bunch of radioactive stuff. The soil is incredibly radioactive. I think in the Russian army dug some trenches out there when they invaded Ukraine, and they all got radiation sickness. So quite active, quite active. So dog runs into the Red Forest, and he starts digging around like dogs do. And of course, you're a little worried. And you measure the background with your dog, without your dog, and then assuming there's no error in, of course, your measurement time frame. Didn't have enough time to really put that in. Does your dog need decontamination? I.e., is there a detectable amount of radiation on your dog? Use a 95% confidence interval since you love your dog, which is not sure if it's a dog or not, really. That's why the question mark's there. Not that you don't love your dog. And 99% is too conservative. This is what Ali was saying, as in, well, we're pushing the limit further back. That's going to make it easier to say that we don't have radiation. Whereas by using 95%, it's easier to say that we do have radiation. So you have two choices. Yes, he's contaminated, or no, he's fine. So let's see here. We got these numbers. So if you want to try and go along, you can go along. So we get these sigmas, of course, nice and simple. The differential on net with respect to total or background is going to evaluate to 1. Why? Because you have net equals total minus background. Differential with respect to background is -1. -1, the square of your error propagation formula is just 1. And derivative with respect to total is just 1, so also 1. So we don't have to worry about our partial differential terms, we can just worry about our sigmas. So net, of course, is our dog minus our background. Net is then this, 12 counts per second. Not bad. And our sigma net, of course, is sigma squared plus sigma squared and square rooted, of course, because the partial terms are 1. So we get a sigma of about 8.12 counts per second. And if we look at our 95% confidence interval, we'll see that, it goes to about -4 counts per second. At 95% confidence, your dog, there's not a detectable amount of radiation. If you love your dog, you should probably still decontam, because that's only really going into a small portion of the negatives, but you wouldn't do it if you were 95% confident. You would do it if you only were 90, 85% confident. Okay, next one. What's this one? Excuse me. You're looking for radioactive rocks to get silly with it. Because searching up how to tell if something's radioactive would leave a digital footprint, you recall what you learned in scientific instrumentation and take some measurements. Which rocks are radioactive? That's me getting silly with it, with totally not a subcritical source multiplication assembly. Do you know what that is? Have you taken kinetics? Are you taking kinetics right now? Okay. Maybe this joke will land better halfway through the semester. And for various reasons, of course, I am not building a subcritical source multiplication assembly. Got to cover your bases every now and then. Let's get into this. Let's get into the data here. So of course we know net is reading minus background. Sigma net is the square root of reading plus background. This is just a nice little skip we're going to use because we are also running out of time. Here's the table. We have rock number 1 at 25 counts per second. Rock number 2 at 1435 counts per second. Rock number 3 at 43 counts per second. Rock number 4 at 36 counts per second. Background at 17 counts per second. And of course, we want 99% confidence because 95 will not suffice for our silliness. What is the net counts? Well, we have 8, 14, 18, 26, 19, and background still 17. What is the sigma on these? Well, we have 6.48, 38.1, 7.75, and 7.28. So we're just doing the exact same thing to all the rocks. We're looking at the reading, looking at the net, and we're looking at sigma net. When I calculate sigma net, is that the square root of net? Absolutely not. The square root of 8 is not 6.48. But we're using that formula that's up there. So okay, let's look at the confidence intervals now. Just by looking at it, I can kind of tell that some of them might not be radioactive. In fact, this one here that's only at 8 counts per second is quite far into the negatives. So it's negative 8.72 to 24.72. You can see there's a big spread, especially at these smaller values. If we look at the 1435, well, the relative spread on that count is not, or that confidence interval is not that large, relatively speaking. So the more counts you have, the less error you have. This is why we like to have high efficiency detectors. This is why working with higher counts is nice, and why working with low counts, especially in environmental monitoring, can be a bit difficult. So I'm going to keep going on because there's actually some more I want to talk about. Rock number 3 is radioactive, and rock number 4 is marginally. So of course, no, we're sad. This one is quite radioactive, so we're quite happy. Rock number 3 is yes, it's radioactive, and marginally for rock number 4. So now, if you're ever in my scenario here, you know how to tell, and you do not need to leave a digital footprint. All right, next one. What's this one? You're building a secret bunker to conduct experiments and to get aforementionedly silly with it. You need precise counting, and you need to remove background. You're aiming for a maximum count rate of 10 counts per second without your equipment. Oh, I forgot to put the curly bracket there at the end. So this is when I started getting really tired, and I think it shows in the slides if I remember anything. So you decide to measure your basement, and will it suffice at 5.32 counts per second background? No error in time measurement and 99% confidence because, again, we're getting silly with it doesn't mean we're going to be unprofessional. 2.31 is our sigma. 5.32 plus 2.58 sigma is 11.3, which is greater than 10. Why are we adding instead of subtracting here?
You want your upper limit?
We want our upper limit. Upper limit, add. Lower limit, subtract. When in doubt, draw your Gaussian distribution. Draw your axes, and then look at it. Okay, does this basement suffice for getting silly with it? No, it doesn't. Well, this is a little frustrating, so let's save ourselves some time and figure out what background reading we need to say get silly with it. So let's start here. Background plus 2.58 sigma background, or square root of background, is 10. If you squared this as is, you would get a mess. But if you move to the other side and you square it, it looks a lot nicer. In fact, you get about this based on your binomial expansion and from expanding that squared term there. So now you don't have any square root b's. I'm very happy. This is just some algebra to show you that you can do extra algebra on top of your radiation statistics. You get this quadratic. You get, through the quadratic equation, 2 roots, 22.14 counts per second. Does that make sense? No, that doesn't make sense at all. But 4.52 counts per second, that's slightly under 5, and we knew 5 was kind of near the limit. So yeah, 4.52 counts per second is your target count rate. So happy searching. Just another example. I think there's maybe one more example before I start talking about gamma spec. Yeah, one more. A nuclear warhead is detonated above Bikini Bottom. Now, SpongeBob is a versatile creature. You know how sponges are. Total dose of 3 millisievert per day is what he can survive. If the background dose was this before and this after, please calculate if he dies a horrible death due to radiation poisoning at 95% confidence. Assume dose is proportional to counts. What are we thinking? What are we thinking here? What's our first step? Do we need to subtract our background, find our net, and whatnot? Ali's shaking his head. Why don't we need to subtract our background, our 0.1 microsievert per hour? Well, it's because, you want to talk?
It's negligible.
Sure, it's negligible. The other thing, Ivan,
Wouldn't it contribute to the dose as well?
it already contributes to the dose. It's already in that 150 microsievert per hour. We're looking at a total dose rate. So that is background and source combined. So we only need to measure total, which means our sigmas are sigma. I feel like that's something a grade schooler would say nowadays, but I'm sorry. Let's move on. We're looking at total dose. We don't need to actually subtract 0.1. It's built into the number here. So let's see. Sigma net is this much per hour. Yeah, that works. Now, this times 24 hours per day, we're going to get to this dose right here, which is about this millisievert per day. And our 95% confidence interval is above 3 millisievert per day. So, what is the conclusion? SpongeBob is going to die a very, very painful death to radiation poisoning. And perhaps, just perhaps, he should have taken shielding design with Dr. Waller. Very good course. I would recommend it. So yeah, we can see here, confidence interval doesn't cross into our 3 millisievert limit. So SpongeBob's gone, man. So who knows what else happened to the rest of Bikini Bottom. And let's move on. I think we're going to talk about gamma spec here. We have about 10 minutes. So we're going to blitz through this, which is good because I got real tired near the end. So we have a gamma spec. How do we tell if we have a statistically significant amount of an isotope based on its peak? So you can tell I had some help drawing, and then a lot of the other drawings I did not have help for, and it shows. So we have here what is called the full width at half maximum. So if we're assuming a Gaussian peak style, we're going to look at from the background area up to half of its peak, and then look at the full width in channels. And that is 2.35 sigma Gaussian. Sigma Gaussian is not, in fact, sigma error. Sigma Gaussian tells you how far the peak is going to extend, not the error on the counts in the peak. It's an important distinction. We are pressed for time. So we assume a peak on top of a nice straight line background distribution, and then we're going to do a stat analysis on it. Steps are find the full width at half maximum. Find the 6 sigma Gaussian range. What is the 6 sigma Gaussian range? That is going from all the way up to here. So we measure well over 99%. So it's plus 3 to, or minus 3 to plus 3 sigma Gaussian. So we're measuring all the stuff in the peak. Next thing is we're going to average some points outside of the Gaussian range. And we're going to draw a line between those 2 points and call that background. Then we're going to find the total counts. Then we're going to just find the background counts by integrating that line. calculate the net counts, calculate the error on the net counts like we've been doing before, and then determine significance. So let's do some examples. Yeah, I got tired. This is a generic nuclear accident. This is the spectra you get. It's just the same image from before. Find the 95, 99 intervals for the cobalt-60 activity. So I'm going to do this in drawings here. You can tell when I started giving up. Here's our spectra. First things first, we're going to look at the total peak heights. We're then going to go to about halfway through the peaks, and we're going to draw our full width at half maximum. We're going to look at how big this is. We're then going to go, okay, full width at half maximum equals 2.35 sigma. Divide 2.35, we have sigma. Then we're going to go, and we're going to find the 6 sigma range based on the sigma from full width at half maximum. This goes up into here, doesn't matter, but they overlap. That's not good. What do? We're going to be doubling up our counts. Well, as a good engineer, you just look at it and you decide where one stops and the other one starts. So there you go. Now we have 2 nice distinct regions for peaks. Are there any questions so far? Briefly, any questions? Good. We can sum up the total counts under each peak, and then we start looking at the 2 values on either end. So I'll come on this side so I'm not neglecting you all on this side. We sum up to 6370, we sum this one up to 4550. I'm pulling those numbers out of thin air, just for the example. But then we're going to take an average alongside this boundary of the counts there. We're then going to take that average number, and we're going to draw a line between it. We're then going to sum up all the counts under that line as our background estimate. This is an estimate. First, we've made an assumption that there is a peak, and that the peak is peak-shaped, and that the background is straight. Now comes a little detail. Since we're looking at cobalt-60 decay, cobalt decays with 2 gammas per cobalt decay. So we're going to need to look at that. And of course, time measurement is a thing. We're not doing error in time measurement today because we have 8 minutes left. So the total is this. The background is this. And okay, so we're good. Notice if we take background before putting a source into our thing, we can just subtract the background. We don't have to do this line estimate. But if you're out in the field and you cannot separate your background from your total counts at the same exact geometry, you have to do the line estimate. Text wall here, don't be scared. I just put it in there for people who clearly haven't shown up to lectures. So for our case, we're looking at the line estimate. Now we'll do exactly what we were doing before. Find our net, find our sigma net, and since cobalt-60 gave 2 peaks for the 1 decay, we need to divide this value by 2. If you look at the variance, or the error propagation formulation, you can convince yourself that yes, you can also just divide sigma net by 2. I don't have time to show you, but I believe it, so you should too, obviously. And we'll keep moving on. So we get a final activity of this with rounding. I know it was 121 before. That was because I rounded up. If you divide the original number, it rounds down to 60. So we look at this. We have a confidence interval at 95% from 3527 to 3763, and 99% to 3490 and 3800. I really wanted to cover that whole process. I'm sorry it was so brief. Again, there's a lot of stuff in these slides. But now you can look through and see the process if you ever need to do it. And yeah, these are radioactive as hell. So whatever time frame you chose, you can add that error in, and it should be good. Again, time today is likely very scarce. Now we're getting to, I think, our last example, which is the racehorse Sakura Bakshino is visiting a nearby stable for a race. I think this is a racehorse from the 90s in Japan. As a prominent nuclear engineer and someone who wants to make bank, you've been hired to make sure the stable provided is up to the standards demanded by this very picky racehorse Bakshino. The demands are as follows. And of course, please help me, NUCL 3740U scientific instrumentation students. It's me, Sakura Bakshino from real life. So, what are the the requirements here. There must be no detectable cesium-137. However, this horse wants a manganese 54 exposure rate between these two values, or he will throw a fit and he will lose the race and you will not get paid. Or maybe you do. Doesn't matter. That's how contracts work. All right. Oh, there's a porpoise up there. I guess don't mind him. That's like a little message in a bottle for myself. It's 2 a.m., need the slides done, and we don't have time, which, yes, we don't have time, so foresight. And please note that all things are in microsieverts per hour. All right, so this is what you measure in the stable. We're not going to do the spectra thing because, again, that takes time that we don't have. Total cesium is 25. Background on the cesium measurement was 15. Remember, because we're drawing a line, the backgrounds for our different peaks are going to be different. Total manganese was 93. Background manganese was 23. This is the peak, I guess. So let's see. Do we have our conditions met? Using our useful fast calculations, sigma net is our reading plus our background. We can get this, and we can find our sigma. And we find that our 95% confidence interval of cesium falls within the limit. In fact, it is negative 2.4 to 22.4 negative. We're good. No detectable amount at 95% confidence. This is good. What about the manganese? Do we have an activity in the specified range? Uh-oh, guys. Uh-oh. That's out of the range. Barely out of the range, but out of the range nonetheless. So you have a choice. You can either be trying to get that bank and lie, of course, and of course the horse will then say, oh, thank you, NUCL 3740U scientific instrumentation students. I am so happy, and I will win this race, and in the fine print, you are going to get paid. But if you lie, be prepared to get hit with the how can I bucksheen in these conditions. And perhaps you go hungry that night. So, thank you all very much. You all know how to calculate these statistically significant amounts of radiation now. Take care.